Okay, so we're going to talk about energy today, so I get to do my fun demonstrations. Energy, like I said at the end of last class period, is really important for this entire class, not just for physics, because energy is what gives us the ability to move things and do things. And so whether we're talking about physics or talking about chemistry or talking about earth science, what was the last one? Chemistry, physics, earth science, or even astronomy, energy is going to be an important concern. So that's why it's very important to talk about. So I started last class period with defining work. Work is force times distance, but there was one more thing to it, not just force times distance. What was the additional piece we needed? Needs to be parallel. The work, so use the symbol, well, my handwriting is on top of it. W for work is force times the distance parallel to that force. So you remember I did the example holding those paper towels. If I'm lifting them up, I'm doing work on it. If I carry them horizontally at a constant speed, I'm not doing work because my force is up and the motion is perpendicular to that. Now, if I lift it up, I'm doing positive work because my force is up and the distance it moves is up. But what else is putting a force on these towels besides me when I lift it up? Gravity. What direction is that force of gravity? Down. So just like with my example of Casey and me, that's the right use of the word there, pushing on the car, if it's moving against the direction Casey's pushing, then she's doing negative work, which means she's removing energy. I'm putting energy in by pushing it goes the same direction. She's removing energy. Or with this, if I lift it up, I'm doing work on it. I'm adding energy, and gravity is doing work, but it's taking away energy. So energy is tightly related to work. In fact, energy and work have the same unit. So let's look at the unit here. What's the unit of force? Newtons. And what's the unit of distance? Meters. So work has units of newtons times meters. But because work and energy is very dominant in physics and everything else in life, we have a new unit that we define, the joule. That's spelled Joule. It's a dude's last name. But the joule is the unit of work. So a joule just means a newton times a meter. Of course, a newton means a kilogram times a meter per second squared. So if you put it all together, that's equal to a kilogram meter per second squared times another meter, which means kilogram meter squared per second squared. So this is the unit of energy using base units. This is the name we give to that using base units. So that's the unit of work and it's the unit of energy. Now, I better get to the work-energy relation real quick or or it will lose some of its importance. I've already talked enough about lifting weights, so we can move past that. Just a question to make sure that you understand. Whoops. Give me a second. I thought I had the right presentation loaded up, but in my rush. So you can't answer yet because of my little problem here. Excellent. Well, let's just go with you can't answer because I know I put them right here where I'm looking in there. Not there. Not there. It's a shared network drive. I put them there. Put them there. Oh, wait, now it just showed up, which is even weirder because it's a shared network drive. It's not a drive on this hard drive. Okay, well, life is better. Close sesame. Don't save that. Okay. I have confidence, blind confidence. So now you can answer.
Actually, I asked if fish have feelings, so.
I feel.
No.
Yes.
Do you?
Oh, no, it's your name. I thought that's what you're saying. No.
Oh, if it's my name, then I'm gonna be in trouble. I don't know.
It is your name.
Oh, crap. Work on the wall. I don't know, work it out.
Choose the one you like think's most. Okay. So we had here 1, 13, 0, and what is that number?
3.
Okay. It's easier to ask you than to do the math. I totally right. Mine, it just shows black. I can't read it. Okay, so we had pretty good agreement. Haley, what answer did you choose and why?
I chose the wrong answer. Same. And so I have no real reason as to why that would work.
Well, tell us which one.
My reasoning was force. You're not, I guess technically you're not doing work, but you're always pushing on the ground. And you're all gravity, force. I don't understand.
Okay, well, I mean, it's fair to be honest, right? So, work is force times distance moved parallel to that force. So when you're pushing on the wall, are you putting force on the wall? Yes. Is the wall moving? No. So you're not doing any work on the wall. What about the ground? Are you pushing on the ground?
Yes.
Is the ground moving?
No.
So you're not doing work on the ground. So both A and C were correct, right? No work on the wall and no work on the ground. Then there's B, no work at all. This one here, I would accept for correct answers either 13 or 3 because there's another aspect that I haven't talked about. In physics, if I had used the word mechanical work, the correct answer would have been B, no work at all. And that's all I've talked about is mechanical work. The force times distance is technically the mechanical work. So what's the difference in all work and mechanical work? Well, our bodies. In the morning, we eat food. And then that food contains energy that our bodies use. And so my body right now is using energy. And that using of energy is work. It's a different kind of work. And of course, if I'm pushing, those muscles are going to get tired, right? Why are they getting tired? Well, because of the energy being expended. So there's, biological work, but no mechanical work. And that's why this one I would have accepted either B or D. So I would accept either of these two because it depends on your understanding of work. Now, a lot of people, if you get tired, that's work. And that's relating more to the biological work. You get tired holding a car up for, 10 minutes if you're, that kind of strong without the car having moved and done any mechanical work. Okay, so now energy. Getting to the definition of energy so I don't confuse things too much by talking about work and energy without defining energy. Energy, my favorite definition of energy is the ability to do work. Right? If something has energy, it can do work. So by the knowledge that I can take this and raise it up, that I have energy. And when I raised this, that energy was converted, and that was the work. So the work was converting energy actually from one type to another. So energy and work are tightly related. And we can have energy for a couple different reasons. Let's take the easiest one to understand. Oh, let's be serious. I got this 1 kilogram mass in my hand. If I take this 1 kilogram mass, that's what I was going to pretend to do, but I won't even pretend. But if I take this 1 kilogram mass and I place it on my finger, is it going to do anything to my finger?
Yes.
I got a no and a yes. That's great. Explain why I said no and explain why I said yes.
It's not that heavy.
It's not that heavy, so?
So the amount of, I don't know, force is like absence. I don't know.
Okay, what was your reason for yes?
Well, I'll use my phone as my counter example. So here's my finger. Definitely a change there. My finger feels kind of squished.
Okay, so it squishes, even with a small weight like the phone, it squishes the finger a little bit. And so there was a downward force on it and motion, so it did work. Not very much, right? But it did a little. I could have made it more. I could have taken, here's 10 kilograms.
All right.
Put 10 kilograms on my finger. I'll have part of it's a part of my finger. It squeezes a little harder, right? And it definitely is compressing, so it definitely did work. So it was able to do work. Why?
Because
Okay, it has energy because that's the definition. It can only do work if it has energy. And then we have to say, well, what gave it its energy?
Weight? No.
Okay? The force of gravity is something, if I took it, if I put it here, we say, okay, it's sitting there. Is it doing any work on the table? It's not doing any. It technically did work when I set it down. Technically, the table had to flex a little bit. It couldn't remain perfectly the same position. The amount it flexed is probably not measurable unless you get something super, super sensitive. You don't have a laser. So there was a little bit of work when I set down, but gravity is pushing down. There's that force. Now, if I lift it up, I did work on it, right? I gave it energy. When I let go, what's going to happen? Which I'm not going to do, of course. It'll fall back down because gravity is going to do work back. And so gravity stores energy that it can then give back. And if something stores energy and gives it all back, we call it potential energy. So when I raise this up, the higher I raise it, the more potential energy it has. And when I let go, that potential energy will be given back in work. And what's it going to make it do when I let go? Fall. Now, getting back to where I was starting, if I take this and I throw it at you, or if I just drop it on my toe,
ow.
when it hits my toe, is it going to do any work on my toe?
Not well, if your toe is like made of metal.
Which it's not. It's made of flesh and bone.
Oh, okay. Well, that's one.
It's going to do some work on my toe, right? When it gets down there, just before it hits my toe, it has very little gravitational potential energy left, right? It's not very high. What kind of energy would it have then? What allows it to smash my toe? What? Okay, the word we use is kinetic. It's moving, and kinetic means moving. So we also have kinetic energy, the energy associated with motion. So two kinds of fundamental energy we talk about in physics are kinetic energy and gravitational potential energy. We'll also talk about springs, because springs can store energy and give it back. So they have potential energy. When we get to chemistry, we'll talk about chemical potential energy. Because when we form a chemical bond between two atoms, the only reason they form a bond is because it's a lower energy state. And sometimes you can take two things that are bonded together and bring something else, and it'll be a lower energy state if you break a bond and make a different bond. And it releases energy, and so it does it because things try to go to the lowest energy state they can. power, question, Brittany.
So the weights we're doing work when you move them and put them on the table, or say you drop it on your foot.
Mm-hmm.
Do those objects do work at all, or no?
Well,
Does the table do work when you put or is that just?
yes. When you put the weight on the table and the table flexes downward just a little bit under that weight, or if you had a weak table, measurable amount, then the table is making an upward force and moving down, so it's doing a negative work.
And the same thing for your toe with that weight.
Yes, my toe would be doing a negative work when it's getting crushed.
It is a negative word.
So they're both doing work.
They'd both be doing work, yes. And in fact, let me put here the work-energy relation. The net work is equal to the change in, remember that capital Greek delta means change in, kinetic energy, where kinetic energy, and we just have to put the equation out here. We're not deriving it because you use calculus to derive it. The kinetic energy, the energy something has because it's moving, is 1/2 its mass times its speed squared. Now notice momentum had to do with mass and speed. Momentum was mass times speed. So you can also write this actually in terms of momentum. Momentum squared divided by 2m is the same thing. So kinetic energy has to do with motion. Momentum had to do with motion. And the momentum was useful to us with the ideas of the impulse of momentum. If I have this much momentum, it's going to take this force multiplied by this time to stop it. Kinetic energy is a measurement of how much work it's going to be able to do when you stop. Do you have another question, Brittany?
Where did that M come from on the bottom?
Okay, where did it come from? Let me show the math to get there.
What is P?
P is momentum. Remember I said I can't give you a reason why P is used for the symbol for momentum. So P is equal to mv. So that means P squared is equal to m squared v squared. And so then if I take that m squared v squared and I want to get it so it just has mv squared, I'm going to have to divide by m on both sides. And then, of course, to get 1/2, I just divide both sides by 2. If you want to do it in a less feeling way, in a more mathematical way, you could have said, well, V is equal to P over M. And so kinetic energy is equal to 1/2 M times P over M quantity squared. And that gives you MP squared over 2M squared.
No, we're good. That makes it worse.
Brandon?
Well, I thought since it's after the p squared over 2m,
Mhm.
I have to take the square root to get rid of that square.
Well,
Divide by 2.
not if I want the kinetic energy. The divide by 2 is because of the 1/2 here.
Oh, okay.
Okay, you had a question, Casey. Was that answered or you still have it?
Oh, my question was just what P was because it was
Oh.
confusing.
Okay.
Also, can we make up our own symbols or is that not?
For things like position, there's a little wiggle room. For momentum, kinetic energy, no. Work, no.
Can't call it KD. P.
Yes. In higher level physics, we call it K or sometimes T, because temperature is a measurement proportional to the average kinetic energy, it turns out, but that gets it even more confusing. Okay, power is the rate, doesn't say here rate, but power is the rate of energy conversion. So rate is amount per time. So that's where we get the relationship, the work done divided by the time. Now this brings you to simple things like, I can, as a child we had to go out and, hoe 4 rows in the garden before we could play. And I would get out there and try to get it done as quickly as possible. So I try to get my work done in a short time. Would that be a relatively high power or low power situation if I'm trying to do my work in a short time? High power. Now, if I'm trying to get my work done in a short time, if I am using, putting out high power, what's that going to make me feel like? Tired. Now, I have a little brother. I love my little brother. He nearly died at Christmas time, which made me really scared. He had a brain hemorrhage. But he's fine now, which is a miracle. My little brother, when he would go out there, he didn't want to hoe. And so he'd be like, he could have been a union worker, sitting there leaning on his hoe for a while. And he would take twice as long to do the same amount of work. Higher or lower power? Lower power. Did he do the same amount of work? Yes. Did he feel more or less tired when he was done? Less tired because of the less power. And so it's the same thing. You can run a marathon and finish in 2 hours. I can walk a marathon and finish in 14 hours. Now, by the time I finish, you're probably going to be feeling pretty fresh. But at the finish line, you're going to be a lot more tired than me because I didn't put out the power, even though I put out the same amount of work. I probably don't feel like walking a marathon either, just in case anyone wants to challenge me on this. Not something I hope to do. Okay, second clicker question. A job can be done slowly or quickly. Both may require the same amount of work, but at different amounts of... That's right.
Check my notes. That's right.
Skyla and Larissa. Does it log you out like in between?
Yeah.
That's really convenient. All right. Hey, this time I can read it. Because nobody answered impulse. Okay, so we had a pretty strong, I'm not going to ask somebody, the definition of power is work divided by time. And if you do it in a different amount of time, it's a different amount of power. So we got that squared away. Now, talking specifically about potential energy. We have gravitational force. What is the equation for the force due to gravity? mg. So the force due to gravity is mg. And if something falls a distance h, then if it falls, is gravity doing a positive or negative work?
Positive.
Ooh, we have two answers. Why'd you say positive, Brandon?
I don't know. That's what I think it is.
Why'd you say negative, Brittany?
Because it's going down.
Okay, here's how we can answer that. Here's my ball. I need to look at the force. What direction is the force of gravity? Now, if it's free, that's the only force. And then what direction is its motion? So are those the same direction or opposite directions? Same. If they're the same direction, then it's positive work. And so it turns out Brandon was right. It's going to be positive because the force is the same direction as the motion. And how much work does it do? What's the force? I hope you said mg. And what's the distance parallel to that force? The distance. I at least thought I heard mg. That's not distance. If you said something else, correct me.
I said 3 meters.
Oh, okay. He said 3 meters. mg is so close to 3 meters. You can see how I misheard that, right? Okay, I'm going to use the symbol h. So the work is going to be mgh to fall a distance h. So in this case, this fell a height of 3 meters. This one here, it rolls down a slope that's 5 meters on this side but a height of 3 meters there. Oh, actually, I guess this one here is the one that fell 3 meters straight. Do they fall the same distance or more or less?
I'd say more.
Okay. The distance traveled is more, but the only distance that matters is the distance parallel to the force. And so the force of gravity is down. Only the vertical part matters. The horizontal part doesn't matter. So the fact that this is 4 meters on this side, because it's a 3, 4, 5 right triangle, doesn't matter. It's going to end up with the same amount of work done by gravity because only the direction parallel to the force matters. So in this, we define the potential energy as, well, it's actually potential energy change is defined as minus the work from the force. But what that gives us is a definition that potential energy is equal to what I have up above, mgh. So when I'm just going to grab a 5 kilogram mass here. When I have this 5 kilogram mass, if I hold it 1 meter above the tabletop, then using the tabletop as my reference for zero potential energy, I can use any point. Using the tabletop for the reference, this has potential energy of its mass, 5 kilograms, times g, 9.8 meters per second squared, times that height of 1 meter. When I drop it, what's going to happen to that potential energy?
Does it change to kinetic?
It changes to kinetic because it starts moving and motion was kinetic, right? So it starts changing from potential energy into kinetic energy. So as it's falling, it's converting to kinetic energy. Here's just some examples of potential energy and things you see. Things like when you stretch a rubber band, you are doing work on it as you stretch it, and you let go and it gives it back. It slams back together. Or if you're into archery, you draw and you are doing work on the string stores that energy. Actually, is the string store it? No, not in a real bow. It's really the bow flexing that's storing it. And then you let go and the energy is transferred via the string to the arrow. And then a raised ram of a pile driver. Pile driver is just, you lift a heavy weight, you drop it down. It hits something and drives it into the ground. Already talked about this, so I can skip over that. Right there's the equation we worked out already. And the work energy theorem is what I already described about the work and kinetic energy relationship. You had a question.
Okay, so when doing the difference between potential and kinetic energy, like the weight has that was the potential energy. So as it starts falling, it turns to kinetic, but does the energy change?
The total energy, this is a good question. When we get to thermodynamics, talking about heat and whatnot, we will learn about the first law of thermodynamics. It says energy cannot be created or destroyed. It can only be transferred from one type to another. So when we have the mass up here, it has potential energy, we let it go, that potential energy gets transferred, and for a level of this class of this level, gets transferred to kinetic energy. When it hits the table, what happens? The table will absorb it, and some of that energy will go into deforming the table. Some of the energy will go into making a sound wave that you hear. Some of the energy will actually make it just a little hotter. Now, if we wanted to be more complicated, as it's falling, it's also making air molecules move. And so it's also going to be transferring some energy into those air molecules as it's falling. But for this level of class, we pretty much ignore that part and just talk about the others. But the energy isn't created or destroyed, it's just moving from one area to another. So this picture here is relating the work-energy relation, which was the work net is equal to the change in kinetic energy. Now, in this case, if you have a car, you might have started with speed initial is, let's just say 20 meters per second, right? I'm using the metric units here rather than the ones you're used to seeing on your car's speedometer. And the final speed, we're going to bring it to rest, is 0. And the mass of the car might be, no, that's too heavy. Let's just go with 1,000 kilograms, a nice even number. I had a car when I was in college that was light enough that I could pick up the back end. So to parallel park, I got lazy, and I would just drive the front wheels where they need to be, pick up the back end, and carry it to the curb. Good old Nissan Sentra. Yes, my roommate was on the football team and was very disappointed that he wasn't strong enough to lift up the back of my car. So given that situation, what's going to stop this car?
Friction.
Force of friction. And if I tell you that it stops in a stopping distance of 15 meters, how could you find how big the force of friction is? This is going to require you to do some thinking and putting stuff together.
What was the question?
So we have a car that starts at 20 meters per second, has a mass of 1,000 kilograms. It's going to go from 20 meters per second to 0, its final speed, in 15 meters. Force of friction is what's going to stop it. How big does that force of friction have to be? How big?
I said 20, but I'm just guessing because I didn't do the math.
Yes, we're going to have to do math. What is our idea, our physics idea? Actually, there's multiple ones we're going to put together here. Go ahead, Brandon.
Wasn't force like mass times velocity?
Net force was mass times acceleration, but that's net force.
Was it the conservation thing or no?
Well, I'll lead you through it.
We're confused.
What we're going to do is take this relation I put here and say the net work is going to be equal to the net force. So I look at the forces in the horizontal direction. I'm not worried about the vertical direction because it's not changing velocity in the vertical direction. So just in the horizontal direction, we just have the force of friction multiplied by the distance it travels, except for one thing. What's that one thing that's wrong?
Normal force?
Work is force times distance parallel. This distance is what we call anti-parallel. Instead of being the same direction as the force, it's the opposite direction. And so that changes the sign. It makes it a negative. And that makes sense because we're taking away energy. Where's it going? Have you ever felt the tires after you skidded to a stop? They're hot, right? That is a place that some of the energy went, the heating. If you left rubber on the road, well, there's another place. If it made a sound, there's another place energy went. And then that's equal to the change in kinetic energy. Change in always means blank minus blank. Which one is the positive? Which one's the negative?
Negative's friction.
Well, no. In just change in. So if I had like change in position would be either initial or final minus either initial or final. Which one is the one that's positive?
Initial.
Final. That'd be. So it's going to be kinetic energy final, 1/2 mass times speed final squared, minus kinetic energy initial, 1/2 mass times speed initial squared. So there's my mathematical equation, putting my ideas of what work is and the work energy relation together. And of course, what kinetic energy is. Now, whenever I solve a problem like this, I leave things in symbols. To me, the symbols are more meaningful than the numbers. I know for you, probably for every single person here, the numbers seem more meaningful than a symbol. And it's something that you develop as you become more comfortable doing physics work. But I always do put in my zeros right off the bat. So my final speed was 0, so I'm going to put that 0 in. And now I just need to solve this for my force of friction. Well, since I have minus force of friction times distance. How do I get force of friction by itself? Divide both sides by minus d. Why minus d? Because I want to get rid of the minus sign as well. So now the d's cancel, the minus signs cancel. Over here, the minus signs cancel. And I'm left with force of friction is equal to mass times speed initial squared over 2 times the distance it slides. So that would be 1,000 kilograms times 20 meters per second quantity squared over 2 times 15 meters. 20 squared is 400. 400 divided by 2 is 200. 200 times 1,000 is 200,000. And 200,000 divided by 15, I don't know. 2 divided by 15, I should know this.
13,333 and a third.
I was right. Just kidding, I said 20.
1.3 times 10 to the, let's see, that'd be,
4?
yes, I believe it's 4.
Wait, what was the
And the units would be
Joules.
actually newtons.
Oh, yeah.
And we can actually look here, kilogram meter squared per second squared divided by meters is kilogram meter per second squared. You had a question, Casey?
what is this the answer to? Is this the friction?
This is the answer to how much force the friction had to be. Yes. All right. Now the actual where in my slides I had kinetic energy defined, 1/2 mass times speed squared. And you can see no reason given because it requires higher math. And the work energy theorem is what I just did. There's no point in spending more time on that. Here's a picture of a homemade pile driver. You tie a mast to a string that goes over a pulley, you pull it up. You're going to use this thing here, which we call a machine, a simple machine, to lift it up. If it's like, 1,000 kilograms, none of us could lift 1,000 kilograms. 1,000 kilograms weighs 2,200 pounds. None of us can just lift that up. But using a simple machine like that winch, we could all lift it up with the machine. The point of the machine is making it so we can, with a force we are able to apply, somewhere else apply a force that's multiplied, that's bigger. And then you just cut the string, it falls down, and look, it bangs that wood right into the ground. It's a pile driver. When you cranked on this winch, you were applying a force and it moved in the direction you were applying the force, so you were doing, what do we call that? You were doing a positive work. And that positive work was raising the mass, so your work was changing the potential energy of the mass. Then when you cut the string, what happened to that potential energy? It did what? Brittany, I know you said this earlier.
What was,
When you cut the string, what happens to the potential energy of that mass?
it turns into kinetic.
Turns into kinetic. And when that kinetic energy, when it's all turned to kinetic energy and it hits the post, what does it do? It transfers as it does work on the post, putting a force on the post, and it moves a certain distance into the ground. Where is it? Okay, only one. I'm going to go right past that to my first demonstration because I don't have a lot of time and I want to get both of my demonstrations in. So for this, it takes me a minute to set it up. I didn't want to have this just hanging up in front of the projector all class periods. That's why I didn't do it before class.
Oh no.
Where is it?
Behind you.
And somebody kindly screwed it in place there for me. Sorry. All right, so that out of the way. I have here a bowling ball. And I'm going to hang the bowling ball.
Is this safe?
Yes, this is perfectly safe.
Hang a bowling ball from my ceiling.
Okay, yeah.
Thank you.
That thing is like mounted It's way over constructed.
Can I take a picture of that?
You feel what?
Snapchat story.
Okay, so I'm gonna take this back here,
Oh, no.
and let's see here.
Oh my
The trick
gosh.
here is I gotta make sure I don't move wrong.
I'm so glad.
Bring it up here so it's touching my nose, right? I let go, what's gonna happen?
It's gonna not slam you in the face. It's gonna slam you in the stomach.
It didn't hit me in the face, hooray! I hate, when I was at PUC, it was set up just right so I could have my back against the wall. Then there's no way I'm gonna step into it. I just keep my head against the wall the whole time. Here, let's say I do this and I'm leaning back,
Oh, no.
and then I let go. After I let go, I lean forward, and now it would hit me in the, right.
Oh!
So, yeah, I worry about it here just because I have to be careful. But, what do we notice here? What happened to the height?
It's not as high anymore. Everything's back.
It's the same.
Oh, is it?
How close is it to my chin?
Okay, can you do it again? One more time.
It's pretty close, but it's about an inch away. So it didn't come quite as high. So now let's describe this. Let's first of all come up with a hypothesis to explain why it came close to hitting me in the chin, but didn't hit me in the chin. Go ahead.
So we lost some energy when it switched over from potential to kinetic.
Okay.
Keep the same.
It lost some energy when it switched from potential to kinetic. Is that a scientific hypothesis?
Yes.
Yes. Okay, so that's the first part. Does it explain why it didn't hit me in the chin?
Yes.
Yes. Is it based on scientific ideas? Yes. Does it make testable predictions? Yes. Yes, it does.
Yeah.
So it's a perfect hypothesis. Not only that, it's also the correct one.
Yeah!
Now, you have your last homework assignment. How many people have looked on Moodle to see the solution to the last homework assignment?
I don't know.
No. If you go back to Moodle, you know where it had the assignment initially. If you click on it after it's due, assuming I've had the time to do this, it will then show you all the answers and explanations. So you can look there and you can see that I disagree with the textbook on that problem. Right? The textbook, if you looked in the back, it had the answers for the problem on which one's a scientific hypothesis. And it said the first and the third ones were scientific. I say nay, nay. Me and John Connett, nay, rest in peace. I say nay, nay because the first and the third didn't give you any scientific reason at all. They just said, like, a plant is green because it has chlorophyll. Well, you need more than that. You need something about how the chlorophyll makes it green. In her explanation, she said because it lost some energy in the transfer, that gave us some scientific reasons. And we can make measurements. We can measure, okay, so how much potential energy does it have when it starts? How much kinetic energy down here? How much potential energy? We can go and we can actually measure and see those predictions, see if it's happening and change different things. Tiffany.
What made it lose energy?
Okay, so what made it lose energy, right? If we're doing an actual scientific study, we're not going to be done when we say, aha, my experiments, show that yes, indeed, it lost energy. We say, what made it happen? And so what did you say, Brittany? Air resistance. As it was moving, it had to move air out of the way. And so that took away energy. And so that's why it lost. If we did this in a vacuum, it would lose no energy and come back to the same height. Except for we have some loss up there as well. Eric. You just can put
transferred into the wire as well.
Yeah. So that's my first demonstration. Now, my second demonstration, there is a homework problem for you to do this yourself, but I can do it too. Now, this is 4 super balls, one on top of the other. Only one of them can come off. It bounces. Does it bounce as high as it started? No. That means it's not perfectly elastic. It's not giving back all of its energy. Some of it, when it's deformed, the energy is used to deform it. So I'm going to drop this. And now the trick is you have to drop it so it stays vertical. I sometimes succeed, sometimes I shoot people.
Whoa!
Is that what you expected?
No.
No. Why is that unlike what you expected?
Well, I thought they were all just gonna fall.
Well, yeah, if I drop it poorly, yeah, they do all just fall. Okay. So she had no faith in me. Good call.
No.
What were we saying back here? I know that's not what you meant.
I just figured that the bottom one they just do all the bouncing and it just bouncing.
Okay, the bottom one will do all the bouncing. Now, to answer this, you can answer with all kinds of levels of complexity. But the simplest complexity is, at this point, we have potential energy of 4 balls, right?
Okay.
So we take the sum of the masses times g times the height. When it hits the ground, the bottom hits first, and we have a shock wave that goes through it, gets to the next one, and transfers pretty much all of the energy to the next ball. And then it goes through that, transfers all the energy to the next one, transfers all to this. So this one comes out with essentially all of the energy of the 4 balls transferred just into it.
Does it make a difference that it's smaller or not really?
Yeah, it does.
So like, say that you were to have it the exact opposite order, how much, what would?
Well, for your homework problem, do that. For your homework problem, you don't have to use the exact balls they do, but essentially a tennis ball and a, careful, you don't want to drop your phone.
Yeah, that would be not good.
Essentially a tennis ball and a basketball. It tells you to drop it with the tennis ball on top of the basketball. Now that you've seen it, what's going to happen? The tennis ball goes shooting up, right? You go to the gym, you say, hey guys, watch this. That's cool, right? You can explain it to them. Well, try doing it upside down like Casey did. See what happens if you put the heavy ball on top and the light ball on bottom.
Just
Wouldn't the heavy ball like just switch around?